everything is gonna be fine. So we stopped at chapter 13 on the graph, and now we are talking about halogenation. I told you that most likely you want to use the enolate rather than the carbanion. Or the enol. So if you want to brominate the alpha carbon, you most likely want to use acidic conditions. Can you see the screen? So would use the acidic conditions. Why? Because you want that positive charge on that carbonyl carbon, so you can do E1. This process right here is an E1. So yes, we're starting with the P step. You do your resonance, you remember PRD. You get your enol, but that enol is what's gonna be used usually as a nucleophile. So this is an alpha substitution. Okay, so you can even call this an SN2, whichever way you want to call it. But you're starting from the enol. Open the double bond. You're putting that bromine on the alpha carbon. I think we described this mechanism yesterday. Then you deprotonate, then you're going to get your product. Notice that no base was used here, so you don't need to worry about the kinetic and thermodynamic. But if this structure was like this, by the way, you would go thermodynamic because you're not using LDA, you're not using a bulky base. That's the one that makes things change. So in this case, you always go thermodynamic because you're going to get the Zaitsev double bond of the enol. That would be the major if it shows up in the test. And in the next slide, I think you'll see how you can go from here and do an E2 reaction. I know you said your exam is comprehensive, so you'll need to remember all these things. So this beta hydrogen here can be removed by a base. And you'll make this molecule that can be used in another reaction we call microreaction. Alpha beta unsaturated ketone is used in micro 1,4 addition. So there's a synthesis coming, going in that direction at the end, yeah. Yeah, I did not finish. I'm sorry, I've been so... Yeah, I'm so booked. So let's see. Yeah, that is exactly what I'm saying here. I thought that should come. You want to get the thermodynamic enol. That is the one that's calling the shots here. Before you get there, this becomes the minor. You want the thermodynamic enol. Yes, yes, yes. But that one can be dictated if we were using another reagent beyond your scope. We don't have another reagent in acidic conditions in your scope that will give you the one on the left. However, I'll tell you that you can use enamines to put the bromine on the other side without necessarily going through the enol. No. Nope. Unfortunately, no. Unless you've exhausted all the hydrogens here, and then you do it one more time, then it will start going there. Because now this one will be occupied, right? Right. So this is what I was telling you. This is alpha carbon. This is beta carbon. We talked about this alpha, beta, gamma. Remember when we started? Is that long chain? Where is it? I don't even remember where it was. We talked about so many things. Well, you remember what I'm talking about. I don't see where it went. So you would show a hydrogen on the beta carbon. And the example here we can use is pyridine. It's a nucleophilic base, but it's so smelly. We never use pyridine as a base in the lab. The whole day I'll be smelling it. Even when I used it in the hood, it still smells. So you will take that out. This is our pyridine. It takes that out, and this goes here, and that goes out. And that reaction, we called it E2. Pyridine is not a strong base, but it will do the job here. Yeah. And then the pyridine itself now will be protonated after doing the job. Remember we said that nitrogen with a lone pair, that lone pair is not in resonance, so it plays the role of a base when we're talking about electrophilic aromatic substitution and determining aromatic compounds. Yeah, no, I know. You know what? We went through the same process and look where we are. We are here. So if we made it, you're gonna make it. And you've been in this type of pressure before and you came out unscorched, so you'll make it. So we call this an alpha beta ketone because the double bond is on the alpha and the beta carbon. And saturation is just presence of the pi bond. Been writing so much today. Writing is gone. We'll use that for another reaction we call conjugate 1,4 addition, microaddition. That attacks the double bond. The nucleophile attacks the double bond of the CC double bond, not the carbonyl like Grignard does. That Grignard does 1, 2. Micronucleophiles do 1, 4. We'll talk about that when they come. I think this is the HVZ reaction. Let me see if they gave it a name. No, that's the haloform. I know the haloform, but this is the HVZ reaction. Let me confirm. I'm wondering why the name was not given. I usually just call it HVZ reaction because the names are just so difficult for me. Yeah, that's the one. The name is you laugh at the name. It's called the Volhard Zelinsky. That must be a Russian or a Dutch reaction. Now you, you see why I don't call the whole name. I just call it the HVZ reaction. So it's a typical reaction that involves the alpha carbon. Step 1, identify alpha carbon. Here it is. I know this is a carboxylic acid, but the carbonyl is what defines the alpha carbon. Now there at the alpha carbon, we are going to use PBr3. Usually we use PBr3 to put an OH on alcohols. Just to remind you, organic one. You want a good leaving group, use SOCl2 to put Cl, or PBr3 to put the bromine. It's the same thing here, but the problem is that it doesn't stop here. It takes you all the way to putting another bromine on the alpha carbon. It's good and bad. And if you hydrolyze, then you're left with the bromine on the alpha carbon, because this is just hydrolysis. The Br2 just adds this. No. The PBr adds that by an SN2 reaction. All in all, you go through an enol. I told you want to use the enol as a nucleophile because we'll drop this lone pair here and attack a Br, and this leaves. We'll check and see if they give the mechanism for PBr3. I know it, but I know most instructors ignore it at this point. So once you have it like this, to get here, the Br minus that fell out will remove this hydrogen. You get to this. Hydrolysis is just the water attacking the carbonyl. We did that in the big chapter. Yeah. So if you're just doing step one, this step, this molecule is gonna go making this, and then this will be converted by water. Yeah. No, it hydrolyzes the acid bromide. The Br away and put OH. Now, if you want to go crazy, now the master's level will take this further and react it with OH minus. And that means both of them will be kicked out. This would be OH and that would be OH. And then would use that to make amino acids and other things. Even this one can be used to make an amino acid in biochemistry. So it can go and go and go and go and go in with other reactions. It just goes crazy. So for us, we're just doing the overview, and then we'll do some problems. You need to just post everything at once. Me, I post I post everything at, let me show you. I'm teaching an organic biochemistry class right now, combined for those who are going to see, you know who CRNS are? Those are nurse anesthetists. So I'm teaching them organic biochemistry at once because they have to have that credit before they go to the program. Those people are working right now. So if I don't give them everything, they'll start complaining because they only study. It's an all online class. They have, yeah. But he might be doing so because he's not sure how far you'll get. That's not happening. I hope you know that. So this is in basic medium. Are we able to put bromine there? Now this is me quizzing you. It's still an alpha carbon, but is occupied. Remember we are talking about alpha substitution. You need a hydrogen. Yeah. So in this case, like you asked before, I'm using this to answer you. Once one side is occupied, you're not gonna go Zaitsev. You have to go Hoffman. It's the only choice. And you don't start with a P step here because you are in basic conditions. Yeah, you actually do D step. Then you can do your alpha substitution by SN2. That's an SN2 because you have a good leaving group. Is this an enol or enolate? What did we determine that to be? With the E, I told you call it an enolate. It's an enol without a hydrogen. You know that. And then you don't need a P step. Huh? Correct. When there's no, or anytime you have this one can be called alkanoate. Yeah. All right. So, and they're telling you that if you have excess, XS is just excess, then you can do it multiple times because you have two hydrogens. Replace the one, that's what we got here. And then you do it again. Your sodium hydroxide plays a role. Then you add Br2. You get both of them there. So there are multiple ways to add bromine on the alpha carbon. Correct. Correct. I had my charger, but I don't know where it is now. How can I lose such a big thing? I had it when we started. I'm telling you. Well, hope the laptop will hold on. Ah, they have another student taking organic too. He's in New York after you. Well, I hope my daughter comes from school. She has bigger eyes. She'll find it. I'll ask her to find it. Okay, so haloform reaction. Anytime you have these pieces right here, that's what we call the haloform. You see how we put two bromines here? What if I have a CH3? What if you have the CH3? In fact, in the lab, we usually do the iodoform test where the CH3 becomes, yes? Yeah. Yes, yes, yes. Is it yellow or dark brown? Whenever you have a metal ketone, there's that color change with iodine. It's coming, I think. It should be. It's not here. Maybe in the next one. But it's the same process. Only that iodine will not do alpha carbon bromination. Remember, this one can give you bromines here. Let me do it here so you will see what I'm talking about. So if you do this reaction here, It's likely to give you a bromine also here, right? I know we did it here, but it was acid catalyzed. You see how the bromine is put there? Then you have a bromine there, and then you hydrolyze, you get this. So that's the same problem here. That is why this alpha carbon here has no hydrogens. Therefore, no bromine is gonna go there. It's the alpha carbon, but it's not reactive. In which case, if you do OH minus again, then you're going to get this molecule. But we don't want that. We just want the carboxylic acid from the methyl ketone. So we make sure you start with an alpha carbon that has no alpha hydrogens. So you get this CBr3 and then OH minus. This right here is a good leaving group. So OH minus will kick out. CBr, no, that's a very strong withdrawing group. It's like CF3, which is why it's a good leaving group. Yeah, it's just the first step. Uh, Let me see. There is a mechanism somewhere. Oh, there's no mechanism here. So let me come here. That's general chemistry. You don't like it anyway. So let's see. If you have CH, I'm just gonna do one step, then you'll visualize it. So let's say you have OH minus. It deprotonates one of the alpha carbon hydrogens one at a time, minus charge because you donated a lone pair of electron. You have now 5 valent electrons on the carbon. Only and only then will you now bring your electrophile, which of course if you want you can convert this to an enolate. By resonance you get an enolate. Let's just go with the resonance thingy because that's the way to do it. And then this will come down and picks up a bromine. You end up with this molecule and you repeat the process 3 times. Yeah, you repeat the correct. Correct. You just use excess Br2 and sodium, and you have your sodium hydroxide anyway. It brings you here. But like I said, this one is not gonna survive. You go through the tetrahedral intermediate. I shout at you on that one. That make sure when you're doing such additions, you always want to force yourself to get to the tetrahedral. Yeah, I think he's giving you chunks of notes, knowing that he's not gonna do everything. That's the reality. Okay. No, not open it. I've been reviewing the 2 exams I gave yesterday. Alex, the website, had messed up some of the gradings. Yeah, and he doesn't know some answers are still correct, so I had to go there and grade it myself. So you see, this is quite the mechanism. So this is just repeated. Repeated 2 more times and you have it. So whichever place you saw the CBr3, that's how it's obtained. You're good with that? I want to open the other set because I think we are halfway. Let's see. What's Neymar doing? I lost. Just says for this class, not every other class, just this. That's what's going on. Is it happening also with the other classes? Oh, yeah, you don't want to rush. Yeah. Let's see. This the new? Okay. So Aldo is not difficult. You just need to know where to stop because it can go to make again the alpha beta unsaturated ketone. For example, this one, you remember how we made our alpha beta unsaturated carbonyl on the ring? No? Okay. Here. I know it's vocabulary and you'll start talking this language soon before the exam. This where the double bond is there. You can make this double bond using this process of alpha bromination, then E2. But the other way to do this, which is the goal for aldo reaction, is to use an aldehyde ender base. You are forming a new bond, and if you keep going, you're making a you're piecing two things together. You see, the new bond is right there. But I want to take it slowly because this will be a good chunk of your exam. Very common area to test and synthesis. So what I was saying is that this molecule can undergo what we call not E1, not E2, but E1CB, which is an advanced elimination reaction that I'll talk about when we do the mechanism. Most people call it E2. That's because they are lacking knowledge in chemistry. I pity them. So you see, you have the alpha beta. Now this can happen to an aldehyde or a ketone. So this is alpha beta unsaturated aldehyde. So I'll be very keen to make sure that you're only doing aldo using aldehydes and ketones. There's aldo with esters, but it's beyond your scope. That's advanced organic. And the goal is to put the OH on the beta carbon. So your knowledge of naming your carbons alpha beta will be very helpful. Your knowledge of naming alpha beta gamma carbons, alpha beta gamma epsilon carbons will be helpful. Correct, correct. And then we can kick it away using the alpha hydrogen. Correct. Thank you. And the reason why I drew it is because we just don't call this aldol reaction. This is the aldol. Why? Because you have an aldehyde part, but even with a ketone, we still call it aldol because the reaction was discovered using aldehydes. So you have the aldehyde part, so ald, and you have the alcohol part, all. No. The main statement is this reaction is more reactive with aldehydes than ketones because ketones are more crowded. for addition on attacking the carbonyl carbon. Ah, this is now too much. Another tornado. We have a tornado alert. Ah, I hope it's not coming this way. So this part right here where I said E1CB, please call it condensation. And therefore this one, the alpha beta unsaturated aldehyde or ketone, is called the aldo condensation product. Other Correct. So if there's usually, I don't know what is gonna do here, but like what was it yesterday or the other day? I was teaching another girl, she's from New York. Her professor never mentioned that heat is required. When heat is not mentioned, you want to stop at the aldo because the next step involves removing this hydrogen. E reactions require heat. So I usually tell my students, if I'm using a book that does not mention it, I tell my students in the test, if I don't put heat, stop at the aldo, the beta hydroxy. If I put heat, you're going all the way to the condensation. It does need heat, but like I mentioned, we'll check to make sure that it's stated. If not, then I'll tell you always assume you're going all the way. Now, here comes the mechanism. We know we are in basic conditions. Are you going to start with a P step? Thank you. So we'll start with a D step, and it's an alpha D. So you'll identify. Step number one for this chapter is always identify all alpha hydrogens. They might be the same, they might be different. This is not an alpha hydrogen, I told you that. And that hydrogen, I'm not going to call it acidic. I told you that. Because once it's pulled out, whether you put a plus charge or negative charge, that thing is unstable. You'd rather put the negative charge. There's a step missing here in the mechanism. I don't like it. You'd better put a negative charge here and then show the mechanism of the resonance to get this one. Yeah, this is stealing 1/2 a point from your mechanism. Okay, so the first thing, if I may draw the whole thing, the first thing is OH minus pulls out this hydrogen to give you the carbanion, this one, and then you do resonance. So once you do resonance, it's gonna take you to the inlet. It's gonna take you here. Come on. It's gonna take you here. And that's not an enol, I told you. There's a negative charge, is an inlet. Why? Huh? Go ahead. Why do we need an inlet? Because inolets are good nucleophiles. This is where students get confused. Call these A. Call these B. So sometimes A can be equal to B, sometimes A cannot be equal to B. So when A equals to B, we call that self-aldo. You're fighting your twin. You get a dimer. When A is not equal to B, because the inolate can attack a ketone, for example, then we call that cross-aldo condensation. In agriculture, because I'm a farmer anyway, I once told you that. In agriculture, sometimes we crossbreed, whether it's plants or animals, just to get a new breed, the way people get mules. So that is cross-fertilization. Huh? Oh, you will know. In synthesis, you will know. They will give you a product that does not look symmetrical. Then you know you need two different pieces. Now, uh something looking similar, yes. You will not get carbonyl, carbonyl, but you will definitely see that the structure, if if you put two carbonyls, the molecule will be symmetrical. So we are using this as a nucleophile. Of course, I told you we always want to start with the enolate or enol, and be sure not to kill this carbon. This carbon right here, most students will ignore it in their drawing of the product. So that carbon is this carbon right here. That was the nucleophilic carbon. That's the nucleophilic alpha carbon. So you're attacking the second piece. Let me see if I can highlight it. Yeah, you're attacking this piece. And that part will be this part right here. You asked about new bond. Yes, there's a new bond right here. And that's what helps me to draw the shortcut, especially once I do my condensation. Here we will not rush it. We'll have to do some examples to make sure you got it. Correct. And you really want to identify it because that's the mistake. 90% of mistakes comes from there. And that arrow, this arrow, if you call this arrow 1, is that new bond right here. Yeah. However, the arrow starts from the double bond. So this is not an alcohol yet. We know that is alpha. We know this is beta. The goal is to get a beta hydroxy. So we do the P step. So the process, if you may, like you said, you can call it DAP, right? Or D alpha S P, because it's a substitution of the hydrogen on the alpha carbon. Whatever will help you remember quicker. Correct. Or that's the same term that we'll use in biochemistry. For amino acids and proteins and sugars, carbohydrates. Not very scary. It's too much information. For that one, we'll not be staying on one slide long. You'll just have to spend time memorizing. Yeah, I cannot do that. Me, I understand, but once I understand, it's in my brain. That's it. So can you tell me where the new bond is in this one? I want to teach you. Where is the new bond? Between which two carbons? Thank you. So if you want me to tell you if this was self, I will not tell you because you already see. Do you see how it's self? Yeah, it's self aldo because it's 1, 2, 3, 4 on this part, and this side, that's where the carbonyl used to be. 1, 2, 3, 4. This is self aldo product. It's not condensation yet because we still have, that's alpha, that's beta. We still have the OH. Just ask, don't. Don't make me ask you again. How old are you? It's dinosaurs like us that we should be forgetting. Come on, my charger, where are you? That's something. See, I found my charger. It's just right, but besides me, my mouse pad was covering it. Ah, yeah. I knew I had it in my hands when we started. That's not forgetfulness yet, though. I just did not pay attention. I don't forget easily. I just have too many cables here. I have my keyboard here, I have microphones. This is my little studio here. Let's see. Okay, because the laptop is going away. So now, what do you say about the ring? Is it self or closed? Yeah. Now these are ketones. So this is another part where you're saying that why aldehydes are favored is just because of stability. For ketones, the equilibrium favors the keto form, unfortunately. If you really want to trap it, you have to condense. Hmm. Which one? Which is the inolate? No, this is the keto form. Okay, so in the product, this was the one that gave you the inolate. That's what he meant. He's just saying that this was the nucleophile, the electrophile. Yeah, it attacked the other guy. The second molecule called this A, this will be a B, and this falls down and attacks this. It opens up. P step is gonna give you the OH. So this is gonna be the electrophile. Yeah. So you can cut here, and oh yeah, you can work this way if you're going retro, yes. And I usually tell students to, starting from this chapter, I usually tell them to call this the donor and call this the acceptor, because this concept of donor acceptor will be useful moving forward. It's accepting electrons, so it's the acceptor, and this inolate is donating electrons. Correct. And yeah, if there's so much heat, you can break apart your aldo product, like this one can be broken going back, because you're breaking CC bonds, which are very stable. Yeah. Now, do you know why the aldehyde favors the product? One is because they are more reactive, but the main point is that ketones, because of crowding, the most likely the shape of the product is not gonna favor the hydrogen bonding. Aldehydes are less crowded, so you're likely to get hydrogen bonding to trap your product. Ketones, there's just structural issues. The OH will be out of line to make hydrogen bonding. Yeah, it's all about crowding, I should say. And also aldehydes are more reactive anyway. So this is now the condensation. I'm glad heat is shown. Very glad. Most no, most books, most professors don't emphasize that, but it's very important to know that if you have heat, you're going all the way. And the process is an E1CB. Let me see. Correct. Correct. And this is the mechanism I don't like. If there's heat, you've stopped too soon. Correct. I've shown you the first mechanism. I did. The alpha D, and then you call this the attack, and then you call this the P. You get to your beta hydroxy. But that does not stop there if heated. Correct. You have to keep going now. So you do another alpha D, and then you do an E elimination. It is because you have a strong base. It's not a good living group, but because you have a strong base, this base, then OH can live. Oh, it will still live, but it will not live by as OH. It will live as water. Yeah, they still. You can also do it by E1 if it's in basic conditions. The mechanism should be E1CB. I started by telling you that authors and some professor will do it as an E2. That's wrong. But because it's drawn in your notes, you adapt the wrong thing. Anyway, it makes life easier for you. So so it's alpha D and then an E. So overall, you kind of went alpha D, A, P to the hydroxyl, beta hydroxyl, then you went alpha D again, and then E of OH, elimination of OH. It's very doable, my friend. Very, very doable. This is way easier than some things we've done before with you. We do have reactions like this in our system, including corruption of rhodopsin, the hormone that is used to help us see colors. Because that's it's retinal. I think it's a modification of retinal, which is an aldehyde, which is able to do aldo, causing mutations. So a loss of hydroxide leaving group is similar to the collapse of tetrahedral intermediate. We talked about that. Yes, I agree. So there's nothing much they are saying here. Only that for me, I wanted this to be an E1CB. But when I say E1CB it means that I would have taken out this hydrogen, put a negative charge, and then in a separate step, kick out the OH. They're just going all the way. And also, here they're pretending that they're making an enolate this side, which is why it's important to have gone E1CB. Let me show you what this means. Then you'll understand what I mean. So you have a hydrogen here, correct? So if you take away that hydrogen without showing resonances, it's gonna get you to this molecule. Okay, okay. Uh-huh. Okay. Yeah, I know time we need to schedule something. So No problem. So this is another way that I was telling you to get an alpha beta that you can use in another reaction called microreaction. So this left, usually a poor leaving group, but in basic conditions and heat, it will leave. This is just a review of what you learned before. Here it's an E2, here it's an E1, and this is what I would have called E1CB, but they are doing it their own way. It's not bad at all. Oh, I forgot. You can get the trans or the Cs. You know why the trans is major? Less crowding. Yeah. But again, PhD level, there's a way we can force it to go cis. Mm, Ketones undergo aldol condensation under more vigorous conditions. Uh-huh. So you see, what you are saying here is that if there is no heating, you're going to get, yeah, and the yield will be so low, it will not react that much. Cor Well, the double bond is not going to show up. And the only thing you get is very little amount of the beta hydroxy. But when you heat, you always get that. So you want to go all the way. All right, so I already introduced to you the crossed aldo, two different carbonyls, two different aldehydes, so you get bunch of products. We'll talk about that next. Let's set up some things here.